So before we actually go into details about how to use calculus of residues to evaluate definite integrals, just thought I'd mention some checks on integrals. What do I mean by that? Well, basically, when you're finding an integral, my advice is don't always believe that you got the answer right. It's easy to make mistakes, especially if you're new to this sort of thing. And I mean, this is true in general for any question, or okay, now you're doing homework questions, eventually you'll be doing exam questions. But this is all, of course, preparation for real life when you're solving real life problems. Obviously, at this stage, someone is looking over your shoulder. That's me, because I'll be marking your homework or giving you solutions to the homework or marking your exams and so on. But eventually, when you solve real world problems, maybe no one's looking over your shoulder. You have to learn how to check things yourself. You should always be critical of your answer, always be suspicious that you might have made a mistake. So these are just some little things that you can do to, you have to, my suggestion is you remember all of these 6 little tips. There might be more. These are the 6 common ones, I think. They should all be fairly obvious things and fairly easy things to check. It takes a few seconds to check. And really, if you don't do these things, it indicates that you're being careless and not really thinking about your answer. The analogy I like to draw is that when you leave a hotel room, the advice is always take one last look round, that you haven't left your phone on the table or something, or left your watch on the table, something obvious. So it's like that with doing questions. Take a last look at the question before you move on to the next question. Think, does this make sense? Okay, so what are these checks? Well, if the integrand, that's the thing you're integrating, is always positive, then it means, and it's always positive between the limits of integration, then the integral itself has to be positive. Similarly, if it's always negative, it has to be negative. If it's real, the integral has to be real. If it's imaginary, the integral has to be imaginary. The answer has to be imaginary. This last one is particularly important. Most of the time, we will be doing real integrals. That is, the integrand is a real number always. The answer should therefore be a real number. All integration is just summing. You're basically working out the area under a curve. So the area is always real. If the curve is above the axis, then you expect to get a positive area. If it's below the axis, you get a negative area. But basically, you should never get a complex or imaginary answer to your integral if it's a real integral, which is what you'll be evaluating most of the time. If you get an imaginary answer or a complex answer, it means you've done something wrong. So don't just leave it. You have to go back and check. Now, if the integral could be of either sign, so its integrand can be of either sign. So in other words, if you plot the graph of the integrand between the integration limits, it's sometimes above the axis, sometimes below, you can still quite often estimate whether the area above the axis is more or less than the area below, and therefore you can probably tell whether the integral should finally be positive or negative. This one will save you a lot of time. Check whether any terms in the integrand are even or odd, and that could help you with simplifying the integral. Okay, so if you've got limits which are symmetrical about the origin, and you're integrating an odd function, then you know that the integral of that odd function is 0. So the integrand might contain a mixture of even and odd functions, but if the limits are symmetrical about the origin, then you can remove all of the odd functions. So that simplifies things. Okay, so this one, the integral should have the same symmetries with respect to the parameters as the integrand. So what are we saying here? Basically, if you've got two parameters, say a and b, and if you can swap a and b and the integrand looks the same, so a trivial example would be, well, okay, it's not that trivial. If for example, you had the integral of 1 divided by x squared plus a squared times 1 divided by x squared plus b squared, okay, and then integrate that with respect to x. So you can see you got 1 over x squared plus a squared, and you got 1 over x squared plus b squared. You can swap the a and b, and the integrand is effectively the same thing. So that means the answer should also be symmetrical in a and b. In other words, you should be able to swap a and b and get the same thing. Okay. This is, again, something which seems obvious, but you'll be surprised how many people don't notice that when they lose that symmetry through making a mistake. Okay, so this one is a little bit more complicated to explain, but basically, if you're a physicist, then you understand this as sort of checking dimensions. So if the integrand is a degree n homogeneous function of the integration variables and the parameters, the integral will be a degree n plus n homogeneous function of the parameters, where m is the number of integrations. So what we're saying is that what's it mean by homogeneous? Well, an example of a homogeneous function is something like x squared plus y squared. So it means that you can think of maybe x and y as both lengths, and we've got x squared plus y squared is an example of homogeneous function because it has dimensions of length squared. Let's say x has a dimension of length, so x squared plus y squared has dimensions of length squared. So it's homogeneous means that there's a unique and definite dimension in the sense of the physical sciences, like meters or something. Contrast this with something like x squared plus x. Now x squared plus x is not homogeneous because you've got a power 2 and you've got power 1 there added together. So that's not homogeneous. In a physics equation, if x was the length, you'd never have x squared plus x appearing in a physics equation because the dimension is not defined. If on the other hand you had x squared plus a times x, then as long as you think of a as having dimension meters as well, then it's homogeneous again. Okay, so if you're dealing with homogeneous functions that you can think of as the parameters and the variables have dimension, then this is a useful check because the dx acts as another thing with a dimension, because really what you're doing when you're integrating is you're just finding the area. So you start off with a if you're integrating, say, x dx, then x has units of length and dx also has units of length, and you get x times dx has units of length squared, the area. So whenever you integrate, each time you integrate, you end up with an extra dimension of length, if you like. Okay, so final one, also important, is to check that the integral exists, i.e. is finite. This is a rather more complicated one and something we will deal with a little bit. What you have to be careful with is that if you decide to split the integrand into terms and then integrate term by term, the important thing is that you check that all of the integrals in those terms actually exist. So what do we mean by exist? Well, basically that they have to be finite. If they're not finite, then you're not allowed to add or subtract infinities. So if that's not the case, then it basically means you're not allowed to split the integrand. Assuming that the integral you're trying to find does exist, it would mean that if you split the integrand and the individual integrals you get don't exist, then it basically means you're not allowed to split the integrand. You have to think of doing it another way. Okay, so I'll now just go into the strategy we're going to be using for using the calculus of residues. So we now see how to use the residue theorem to evaluate various types of normally real definite integrals. So the idea is that we have a contour, so we're going to use the residue theorem, which involves a contour on the complex plane. And the contour normally is made up of the integral we wish to find, or a multiple of it, and integrals that we know how to find the value of. And normally those integrals are integrals that just tend to zero. So once we've worked out what basically we can express the contour in terms of things that either we want to find, the integral we want to find, or things that we already know. And then that contour integral will be equal to 2 pi I times the sum of the residues of the poles which are inside the contour. Okay, so that's the basic strategy. All will become clear if you're not familiar with this when we work through and do examples and so on. Put this in bold font. Always draw the contour. It's very important to explain exactly what you're doing. Even if it seems obvious to you, you have to explain to other people what contour you're using. You may as well, so if you're going to show the contour, you may as well show the poles. Be clear which of the poles are inside the contour. These are the more important ones to show. You don't necessarily have to show the poles if they're not inside the contour, but definitely you should show all the poles which are inside the contour, and any branch cuts, if there are any. And always start from the residue theorem. Don't try to memorize formulae. There's too many formulae to memorize if you do that. I would recommend starting from the residue theorem. The things you have to remember are which type of contour to use for which type of integrand. So you should get used to the sort of recognizing what integrand is likely to give you what type of contour. This is really the main thing you have to get practice at, working out what type of contour to use. There's about roughly 5 different types of contour that you need to know about. So you have to decide which one you're going to use. But yes, if you're answering the question, you have to draw the contour. You must draw the contour and make it clear where the poles are. And there's various other little details I'll stress when we do examples.